Welcome back. Today we're going to look at the surface area when we take a region in the xy plane and revolve it around the x or the y axis. In previous sections we've taken a region in the xy plane and made a volume of revolution and found the volume that's inside. So if I would take this region and rotate it around the x-axis, we can get a volume. What we're going to look at today is the surface area, what it would take to paint the outside, essentially. Now, in the end, we're going to end up getting a formula that's all you have to actually know how to use and apply, and we'll look at some examples. And I'm not going to go through all of the details that we use in getting the formula. I just want to give you a couple of the big ideas and talk about how we get there and then how we can use it. And so the first idea is that if we take a surface area, and what we're really looking at is the outside edges. And if we take the outside edges of this region, we're going to get a circle. When we looked at volume, what we did was we found the area of that circle, the area of that disk, and used pi r squared, and then integrated it across the region. Since we're looking at surface area instead, we just want the outside of that circle rather than the inside, and so we need to look at the circumference. And the circumference of a circle is 2 pi r. And what is the radius? The radius of that circle is really just the function height. If we look right here, the radius of the circle that I get when I rotate it around is the height of that function. So we're going to see this 2 pi f at x in our final formula. We're going to be integrating across from a to b, whatever a and b are, but there's one other piece that's not as obvious as to why it's there, and I just want to give a few words about what happens. The issue is that we also need to take into account the fact that this is curving. The function actually has some curvature to it and moves up. If not, then we would just be looking at something that's going straight across. So what we really have is something that looks like that, right? So not just 2 pi times the radius and then a straight across. We also have a curve that has some depth to it, and it's not just a straight cylinder. And the way that plays out when we actually work out all the details, the details are in the textbook, and you can check that out and ask me if you have further questions about it. But the way that plays out is we need to also include a factor, a term that includes the arc length of this curve. Because if not, then we're just assuming that it's going straight across. And so really in the end, what we get is this formula. The surface area of a region from a to b will be the integral of this 2 pi f at x. That's what we got right here, the circumference of the circle. But then we also have that factor that gets me the arc length of the curve between the 2 points as well. 1 plus f prime at x squared dx. And again, the details of this are provided in the textbook. Let me know if you look at that and have further questions. You're not going to have to be able to reproduce that to prove it or to show that it's true. In the end, we just have to be able to use this formula and apply it to certain types of examples and questions. And so let's go ahead and do that. Suppose that we have x cubed over 13, and we're going to take that. And we're going to look at it from 0 to the square root of 13. That's where we want to look. We've got so x cubed is an S curve shape. Dividing it by 13 just contracts it, so it's still essentially an S curve shape. And we want to go from 0 to the square root of 13. So this is the basic shape that we've got. If we rotate that around the x-axis, then we've got that funnel shape, a familiar looking funnel shape. And we're asking, what is the surface area? That's what we want to know. So let's look at our formula. The formula is integral from a to b of 2 pi f at x square root of 1 plus f prime at x squared dx. So the f at x is given, x cubed over 13. The a and the b are given, 0 and square root of 13. We do need to fill out the inside of those pieces. So that 1 plus f prime at x squared. Well, f prime will be 3 over 13 times x squared. So 1 plus f prime at x squared is 1 plus 9 over 169 x to the 4th, and then square rooted. So let's put that formula together. Surface area will be 0 to root 13, 2 pi, f at x is x cubed over 13, square root of 1 plus 9 over 169 x to the 4th dx. And it looks a little bit complicated, but we have to just remember some of our basic ways of finding antiderivatives, and the U substitution from Calc 1 and Chapter 6, the end of Chapter 5, will work in this situation. If I let U equal the inside, 1 plus 9 over 169 x to the 4th, then du will be, the 1 goes away, 9 over 169 is a constant, then multiplied by 4x cubed. The nice thing about this is I have x cubed and I have x cubed. So here's what we're going to do. We're going to take this 2 pi and this 13 all the way outside of the integral. We want to see x cubed times 36 over 169. So I'm going to put this 36 over 169, the 9 times 4, inside the integral, but I just sort of put it there so that I can end up making this stuff, the x cubed, so that the x cubed and the dx, so I can see du showing up in there. Right, so at this point, what I've done is I've just by magic taken the 36 over 169 and put it inside the integral. In order to do that, I need to undo the 36 over 169 by multiplying by the reciprocal out front. 169 over 13, it's got to show up outside to undo what I've put inside. And then this becomes square root of u. So I'll leave it as it is right now, square root of 1 plus 9 over 169 x to the 4th dx. And now the point is that this stuff together is du, and this is the integral of the square root of u. So 169 over 13, sorry, that should not be 13, that should be a 36 right there. We put in a 36 over 169, and we need to take it out by taking 169 over 36. But 169 over 13 is 13, so this is 13 times 2, which is 26 over 36 pi. That's what the outside looks like. The inside, the stuff in the box is du, and this is the square root of u. So that will be square root of u du, which is 13 over 18 pi. Square root of u is u to the 1/2, so it integrates to u to the 3/2 over 3/2. Right, add 1 to the exponent, divide by the new exponent. So that's 13 over 18 times 2/3 times pi times u to the 3/2. Well, u is this mess right here, 1 plus 9 over 169 x to the 4th. So that's all raised to the 3/2. Simplify our fractions. 2 over 18 is 1 over 9. So I get 13 over 9 times 3, which is 27, times pi. 1 plus 9 over 169, x to the 4th, raised to the 3/2. All evaluated, so remember this was really all evaluated from x equals 0 to the square root of 13. So 13 over 27, pi, 1 plus 9 over 169. X to the 4th, when I plug in square root of 13, is root 13 times root 13 times root 13 times root 13, which is 13 times 13, which is 169. All raised to the 3/2, minus what I get when I plug in 0. When I plug in 0, this becomes 13 over 27 pi times 1 raised to the 3/2, which is still 1. So this does do a little bit more simplifying. 169 over 169 is 1. So I end up getting 13 over 27 pi times 1 plus 9, which is 10, raised to the 3/2, minus 13 over 27 pi. And we're almost done. 10 raised to the 3/2 is 10 cubed, the square root of 10 cubed. So 10 to the 3/2 is the square root of 10 cubed, which is the square root of 10 times 10 times 10, which is 10 times root 10. So we end up getting 10, or 13 over 27 pi times 10 root 10, minus 13 over 27 pi. Which we could write, if we'd like to simplify it just out a little bit more, we could factor out the 13 over 27 pi times 10 root 10 minus 1. And we've got an answer. So the hard part for these problems is not setting up the integral. That's fairly straightforward. The hard part can be finding the antiderivative, especially when it's kind of a mess with a bunch of different constants flying around. But let's look at another one.
And now we're going to take a look at using technology to answer some of the questions that involve surface area. This technology we'll be able to use to help out in many of the questions that we see throughout the rest of the course. But as with any technology, you've got to keep in mind what it's useful for and what it's not. Many questions I'll demand that you show me the calculus work. And so what I'm about to show you will be very good for checking your work, especially on homework, making sure that you get the right answers. But you have to be comfortable with getting to the answer without the use of this technology. And so what we're going to use is a program called Mathematica. And this is something that every Oakton student has access to. And so I'm going to show you how you can get that and then demonstrate how we'll actually use this program to answer some of the more complicated questions that come up. And so the first thing to notice is that this is the way that you'll get access to Mathematica is to go to My Courses through My Oakton, scroll down to the bottom, and you'll see a Mathematica request form right over here. So as a student, you'll just go into this, follow the link, follow the directions, and it will show you and give you access to download Mathematica and then use it for the remainder of the semester in all of your courses. And so let's actually use the program. I'm going to show you a couple of the basic commands, and then as we go through the course, I'll add to our list of commands that we can use with Mathematica. and we'll use it to answer some of our questions. So let's look at a few of the surface area questions that come up. All right, find the area of the surface generated when a given curve is rotated around the x-axis. So this is one that we looked at, a similar question we looked at by hand just previously on this video. So we'll get to Mathematica. When you open the program, let's open it from start. When we open it up, this is what we'll see. Let's see, they'll go to a new notebook. And it just looks like this. It looks pretty blank for right now, which is fine. So what we're going to do is we're going to use the function that's given over here. Let's remember our formula. The formula for the surface area is the integral from a to b of 2 pi times the function times the square root of 1 plus the derivative of the function. So we're still going to have to know the formula, and we're still going to have to take derivatives that are necessary. So for this function, the derivative of this function is 3x squared over 16. And so we don't even have to simplify. We can, but we won't have to. Mathematica will do most of that work for us. We're trying to integrate. And so the commands are as much as possible, as straightforward as possible. The syntax for all of these, though, is when you have a command in Mathematica, the first letter will be capitalized. Most of them will be just what you expect them to be. So we're going to integrate. Integrate. All right, so integrate is the command. We've capitalized it. The braces are what separate what goes inside a command. So we're going to integrate this function. So, but remember, it's 2 pi. So I'm going to write that as 2 times is the asterisk. Pi is a special character, and we capitalize that. 2 times pi times the function. The function in this case is x cubed over 16. So that's 2 pi f at x. Then we need to multiply by the square root of 1 plus f prime at x squared. So the command for square root is capital SQRT. And when you start typing, you see options show up below. So square root, remember braces are what separates what goes in the command. So square root of 1 plus the derivative of that function. And the derivative of that function is 3x squared over 16. Now, we've got to be careful with our parentheses because it's 1 plus the derivative squared. So now, if we're looking right in here, this is 1 plus, this is the derivative of the function, that's f prime at x, all squared. So now, ending it, the brace ends the square root. Right, so now, if we look at what we got 2 pi, this is the function, times the square root of 1 plus the derivative squared. And that's the formula that we need to find the surface area. The next part of the syntax goes like this. So we've ended the function. This is what we're integrating. Essentially, we need to tell it the limits of integration and the dx. And the way that works is the variable goes next. So we have comma, and then the limits and the variable will all be one piece separated by a brace. So brace, x gives me the variable. That's essentially taking the place of dx. And then we want our limits of integration. So 0 and 4. So and the brace. So there's two pieces to this command integrate. Takes two things, a function, and then a list that gets you the variable and the limits of integration. And finally, we need to end the brace, which ends our integrate function. And then hit shift and enter at the same time. Shift and enter at the same time. And it gives you an output in not in numeric form, right? So this gives me a symbolic output, which is actually what MyMathLabs generally wants. So notice that looks very similar to the one that we did on the board. That's because the one that I did on the board a minute ago was similar with just slightly different numbers, but we get the same basic idea out of that. If you enter this into MyMathLabs, it will give you it will say that it is correct. So let's just check that out and make sure. So if I just enter 16 over 27 times -1 plus 10 square root of 10, then pi, outside the square root, sorry about that, I missed my parentheses. My parentheses in there, I didn't want parentheses to be inside the square root. There we go. And we've got the right answer. And so this will simplify the work when possible. So do just keep in mind that the way that you're going to see questions on exams are very similar to what you'll see on the written quizzes, where you will have to show your work. However, for the most part, what I'm asking you to do in Chapter 6 is to set up the integral. If I see you set up the integral in Chapter 6, then that's what I'm happy with. When we get into Chapter 7 and we're looking at techniques of integration, we're actually practicing and learning how you find antiderivatives. So you will have to show me that. And it's not good enough to actually get to just an answer. You'll have to know how to apply the different techniques of integration. But so that will be clear on the question whether I'm asking you to show all of the calculus, how you find the antiderivatives, or whether I'm asking you just to set up the integral. For 6.5 and 6.6, I will always be okay with just setting up the integral. And you will not be required to complete the finding of the antiderivative for these. And so the use of Mathematica is very much okay and encouraged. Let's try it with another question. So again, we need to do something very similar. And we'll see there's a little wrinkle at the end as far as Mathematica is concerned, but the idea is the same. We have the function, we have the limits of integration. So let's just see what we have to adjust over here. The entire function is going to be changed. So we don't need any of that. So the function will be 2 pi. So I type that in. So 2 times capital Pi, and then times 1 over 18. So now this is the function, e. So e, there's something special for e. I can't just type e to the 9x. The way that we have to make this work in Mathematica is as follows. We need to type exp for exponential. This is an exponential function, 9x. So this right here that I typed, exp 9x, means e to the 9x in Mathematica. So there's e to the 9x plus exp negative 9x. So there's 2 pi times the function. Then we need to multiply by the square root of 1 plus the derivative squared. So we know what to do with the square root. SQRT for square root, brace to start the square root, 1 plus. Now we're going to need to square the derivative. So let's put parentheses there because I know I'm going to need to square the entire derivative. And so this is something where we still have to take by hand. We need to take the derivative of this function over here by hand. Well, the derivative of that is going to be the 1 over 18 is just a constant that goes along. And then the derivative of the two pieces that are inside. Derivative of e to the 9x is 9 e to the 9x because it's e to the exponent times the derivative of the exponent. So that's 9 e to the 9x is exp 9x. And then close brace. So that's the first thing. And then the second one is negative 9 e to the 9x. So that will be minus 9 exp negative 9x. We've ended our exp. This parentheses will end the e to the 9x and e to the negative 9x, and you'll see it get highlighted where it ends. This ends the next parentheses ends the derivative of our original function, and so we need to square that. So now we've ended the function, now we've squared that, and now we need to end. Notice at this point it's highlighting that we're at the square root, so we need to end the square root with an ending brace. Now at this point we're matched up with the integrate, and we would need to end that, but we can't end that yet because the next thing that we need is the variable and the limits, and they're different for this problem. The variable is x, but the limits in this case will be negative 3 to 3. And now we're okay. Shift enter, don't forget the shift enter. And then we see something that we haven't seen yet, this sine h. That's actually coming in just a section or two. It's a hyperbolic function, and we'll see lots of information about it. But for right now, we can actually convert that back into exponential functions. This e to the 9x and e to the negative 9x has a special name, a hyperbolic sine function. We don't have to worry about that quite yet for a few sections. We can get rid of it in Mathematica so this is a hyperbolic trig function. We want to convert the trig back to exponent. So the command that we'll use here is trig to exponent. We want to convert that back to exponent. And what I want to do is take the previous result. So on a TI calculator, that's just like using the answer, A and S. But the way that we do that in Mathematica is with a percent sign. So shift 5 pulls the percent sign up. That means take the previous result and apply our command to it. So this is saying take the result that we have. It's in trig form, a hyperbolic trig form. We want to convert it back to exponents. Shift enter, and then this gets us a result. So if we put that over into our answer, 2 pi over 3 minus pi over 162 e to the 54 plus e to the 54 pi over 162. And it likes our answer, and we're good to go. So this is going to save you a lot of work on weird integrations. If you look at the examples, they get kind of tricky. They definitely do. And I am okay with us just setting up the integral and using technology to find to evaluate that antiderivative. Really, in any of the stuff that we've got in Chapter 6, I'm only worried about getting the integral set up. That's the hard part. Well, it is definitely hard to find the antiderivatives, but the important part is making sure that you set up the integral correctly. And then after that, we're happy to use technology when possible to find the results that are necessary. Again, in Chapter 7, we'll be focusing on finding antiderivatives, so you'll have to actually figure out and understand how to apply all the rules that go into finding these antiderivatives. But for now, Mathematica is a great tool. And so let me know if you have questions about its use. And see you next time.